All right, the first practice problem I wanted to take a look at is question 25.40, which asks us to draw the Zwitter ionic form of L-valine and L-tryptophan. So remember, the Zwitter ionic form is the form that's going to predominate for an amino acid like valine at physiological pH, because at physiological pH, which is around 7.3 to 7.4, the carboxyl group is going to be deprotonated because its pKa is around 2, whereas the amino group is going to be protonated because its pKa is around 9 to 10. So if we want to draw L-valine, which is the naturally occurring form of valine, we start by drawing our carboxyl, put a negative charge on it. Then we put our amino group pointing down on a wedge like that, and we end up with our Zwitter ion, and our valine has an isopropyl group as its R group. So there's the Zwitter ionic form of valine. And if we want to do the same thing for tryptophan, well, tryptophan looks something like this, where we have our amino group going down. So there's our Zwitter ion. The R group in tryptophan is what I told you is called an indole ring. So you've got a 5-membered ring, and then it has a 6-membered ring fused directly to it. It's aromatic. We've got a nitrogen here, and that would be the Zwitter ionic form of tryptophan. Now, something that's interesting about both of these, both of them are L, and they both have the same stereochemistry. Look, if you look at the stereochemistry of valine very quickly, we start with 1, we go to 2, and then 3. So if you go backwards this way, because our hydrogen is in the back, it has S as its stereochemical configuration. Then if you go to tryptophan, you do the same thing. You go from 1 to 2 to 3. The hydrogen is in the back. We're going counterclockwise. So again, tryptophan is also S. When you look at question 25.41, it says the 20 naturally occurring amino acids in the table are all L-amino acids. They all have the S configuration, with the exception of glycine that has no chiral center. Naturally occurring cysteine is an L-amino acid. However, it doesn't have the S configuration. If you look at alanine, again, you go from 1 to 2 to 3. So it is S. You go to tyrosine, it goes from 1 to 2 to 3. So it is also S. The only outlier is cysteine. And this is one that I think is a good idea to know. It's the only one that's not S, it's R. And the reason why is, yes, we start on the nitrogen because it has the highest atomic number between the nitrogen, the carbon, and the carbon. However, if you look at this carbon, it's attached to 3 oxygens. And if we look at this carbon over here, it's attached to a sulfur and 2 hydrogens. Well, clearly, sulfur has a higher atomic number than oxygen. And so now we have this carbon, which is number 2, and this carbon, which is number 3. So we go from 1 to 2 to 3. Our hydrogen is in the back. And so cysteine is the only amino acid that has the R stereochemical configuration. A good exception to know. Next, I want to take a look at a question that is about glutamic acid. So I'm going to write down the structure of glutamic acid. So this is question 25.47. And I'm going to start by writing down here glutamic acid. All right, if we look at glutamic acid, it has an acidic side chain. And I'm going to write down the pKa values of all the protons. This one is 2.19. I should draw the protonated form, shouldn't I? There we go. So this one is, what is it? 9.67. And then this one is 4.25. All right, if you're wondering how I knew which was which, I had the three values. Remember the one that's part of the amino acid nucleus, the NCC, that carboxyl always has a pKa of around 2. The protonated amine is always around 9 to 10. And so the other one is closer to the acidic pKa, so that must be the side chain. Okay, so now what they want us to do is they want to draw the form of glutamic acid that's going to predominate at a pH equal to 1.9. That's a very acidic pH, okay? Very strongly acidic. And you can see that this pH is lower than all of the pKa's in the glutamic acid. Therefore, to draw the form that's going to predominate at a pH of 1.9, all I have to do is copy this and paste it here. This. And then I'm just going to delete all these. Oops, like this. I think it would have been easier to just redraw it, huh? And there we have it. So there's the structure of glutamic acid at a pH of 1.9. Everything is going to be protonated. Next, it asks us to draw the structure at a pH equal to 2.4. Well, now we're at a pH that's higher than this, right? It's more basic than 2.19. That means that that proton is going to be removed because we're in a more basic environment. And so it's going to look like this, where I have the carboxylate here. We're in a more acidic environment than the pK of this proton, and we're in a more acidic environment than the pK of this proton. Give me a thumbs up if you follow me on that. This is a question we ask in nursing chemistry a lot, just looking at pK values and drawing the structure. Okay, cool. Why don't we try one more? What if it's at a pH of 5.8? So if we're at a pH, let's see here, C pH is equal to 5.8. Well, if we're at a pH of 5.8, that means it's going to be more basic than this proton and this proton. And so what we end up with is a structure where the two carboxylates are deprotonated. So we end up with this, both of the carboxylates are deprotonated, and the amine is still protonated. Good. All right, that's something that I think everybody should be able to do. The next question I want to try is 25.59. So this is question 25.59, which looks like this, where we have a phenyl group. Looks like this. And we're treating this first with bromine and PBr3. And in the second step, we're treating it with water. The last step, we're treating it with excess ammonia. So you might remember that this is the Volhard-Zelinsky reaction. What we end up making in the after the first two steps is we end up making an alpha bromo acid bromide. There we go. So we have our bromine here. And then we hydrolyze that with water. So that's after the first two steps. But then when we treat that with excess ammonia, we end up with an amino acid. It's racemic, but hey, it's still an amino acid. So we end up with this. There we go. All right. And could anybody identify this amino acid? This would be phenylalanine. So phenylalanine. Yep, phenylalanine. Let's try the next one, another synthesis problem. Next one is a Stracker synthesis, B. So this is 25.59 B. We're starting out with this aldehyde. And in the first step, we're treating it with, I'll just leave it like this because I'm going to draw the intermediate. We're treating it with ammonium chloride and sodium cyanide. Sodium cyanide. So what we end up with is something that looks like this. So I'll flip it over just to make it a little easier. We still have our hydrogen here. We end up with an alpha aminonitrile. What this is called, this is after the first step. And then in the next step, we hydrolyze the nitrile to a carboxyl group, and we end up with this. So let's draw it very carefully. We have our carboxyl group, right? This carbon is this carbon right here. Then we have the alpha carbon, which has a hydrogen, and it also has the NH2 attached to it. Then we have the methylene and the phenyl. So we have the methylene and the phenyl. And what do you know? Recognize this amino acid? It was the same amino acid that we drew in the last example. This is also phenylalanine. So this is the Stracker synthesis. So Stracker synthesis. So we've got Stracker, we've got the Helvell-Hurd-Zielinski. And for the last one, we have an amidomelinate synthesis. So this is 25.59. And we're starting with diethyl acetamidomelinate. So we start with this compound, like this, like that. In the first step, we're going to treat that with sodium methoxide. And then we're going to treat it with methyl iodide. So that's going to give us this compound where we have that methyl group installed in between the two carbonyls. So now we have a methyl group, and we still have our acetyl group, like that. And then in the last step, we hit it with acid and we cook it up. And that ends up making a dicarboxylate, but then that undergoes a decarboxylation reaction. And the part that's going to end up in our amino acid will be this. I don't know why I drew it like that. It's going to be this part here. That's the part that ends up in our amino acid. The rest of it all is hydrolyzed, so we end up with the protonated form of everything since we're in a strong acid. There we go, and we end up with alanine. Here you go. And that's the amidomelinate synthesis. The next one I wanted to try with you is 25.66, which deals with this compound called methionine and kefalon. And we looked at it earlier on, and it asks us to draw a bond line structure of methionine and kefalon. So it's got a tyrosine, and then the next residue is a glycine. The next one is a glycine. The next one is a phenylalanine. And the C-terminus is a methionine. So we're going to follow the same steps that we did in the lecture. We're going to start with our N-terminus because our N-terminus is on the left-hand side. And our C-terminus is on the right-hand side. And we're going to start. So we're going to write N-C-carbonyl, N-C-carbonyl, N-C-carbonyl. So that's 3. N-C-carbonyl, that's 4. And then N-C-carbonyl, and that's 5. First thing we'll do is we'll complete our C-terminus and our N-terminus. So we'll put a carboxylate here. We'll put the protonated form of the amine over here. And now we're going to add the R groups. Remember, anything that's pointing up is going to be on a wedge, and anything that's going down is going to be on a dash in order to give it the correct stereochemistry. So let's start by putting in the tyrosine, which is like a benzyl group in a way. So it's like you've got a benzyl group like this, and then you have a hydroxyl that's para to the methylene. Next one is a glycine. There's no chiral center, as is the next one. There's no chiral center. The next one is a phenylalanine. So we've got this one, this one, this one. Okay, now we need a phenylalanine. So the phenylalanine, since it's pointing down, is going to be on a dash. It's going to look like this. And the last one is a methionine. Since it's pointing up, we have to have a wedge like this. So we've got CH2, CH2, sulfur, and then a methyl group like that. Now the only thing that we're missing are some hydrogens that still haven't been drawn. Put a nitrogen here, or sorry, a hydrogen there, 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 and we're done. Just like that. Drew the structure of methionine and kefalon.